So you can rewrite that as a matrix times a vector of unknowns, right? The difference is that, well, for one thing, I mean, this is generally, you can let it be rectangular, right? You'd say, well, we could just consider n equations and n unknowns. Then it would be square, fine, right? Well, one of the big differences is the attitude matrix relates a frame to the Cartesian frame, right? So like, for example, these are numbers, right? If this is a linear equation, those are numbers. That's one thing. But in contrast, we could have something like E1 is, oh, I don't know. I'll be lazy. Cosine theta, E1 plus sine theta, U2, right? E2 minus sine theta, U1 plus cosine theta, U2, and E3 is equal to U3, right? This is the polar coordinate frame. And the attitude matrix here is as follows. Right? This is the attitude matrix A. Notice that it's not constant. I mean, theta depends on the point. It's a matrix of functions. So it's very different in that sense. But, you know, you can assign matrices to a lot of different things which aren't systems of equations. In linear algebra, you learn about like linear transformations, right? So there you have a matrix, but it's not a linear equation, right? You can also talk about quadratic forms. Do you guys ever talk about quadratic forms? Do you know what a quadratic form is? Quadratic form there are various definitions, but one you could take would be Q of x is equal to x transpose AX, where A is symmetric. Not orthogonal, but symmetric. For example, you could have, you know, Q of x equal to x1 plus 2x1 x2 plus 3x2 x2. Like that's a formula for a quadratic form. And if you want, you could write that as x1, x2, that row vector times a particular matrix times the column vector x1, x2. And that matrix would be 1, 1, 1, 3. You can multiply out that row matrix column product, and what you'll get back is x1 squared plus 2x1, x2 plus 3x2, x2, or x2 squared.
Yeah, just a FOIL of a square, right?
Right. But my point to you is that's a matrix. It's not a matrix for a system of equations. That is a matrix for what's called a quadratic form. And you can choose them to be symmetric. And so that means you can use this thing called the real spectral theorem. You can find an orthonormal eigenbasis for them. And you can always write the formula as a weighted sum of squares, where the weights are the eigenvalues of a matrix. But we may or may not teach that in linear here, you know. But the way, if you look at the matrix of a quadratic form, it's very different than if you look at the matrix of a system of equations, or if you look at the matrix of a linear operator, linear transformation, in the sense that if you change coordinates, right, if you use a different basis, the way that the coordinate change happens for the matrix of quadratic form is very different than the way the coordinate change happens for the matrix of a linear transformation. So like, it's just something to be aware of yes, there is a system of equations that underlies a given matrix, but it may or may not be the right thing to think about when you see that matrix. That's all I'm saying. I don't think this is on the test. Anyway, so let's take a 5-minute break, and then I'll dive into chapter 4. So, sound good? Or do we need a 10-minute break? Audrey looks like we might need a 10-minute.